Welcome to part 2 of this motion detection series. In this part, we're going to use optical flow to detect motion in a video. So optical flow is the process of detecting pixel motion in a sequence of images, and in this case we're going to use dense optical flow. Now I have an example of dense optical flow right here. We have two images right here that are sequential, and you can tell that these cars are moving because in this bottom left right here, the bumper is at about 1,000. And then on the next image, this bumper is almost basically off the image, right at about 1020, or the max limit of that vertical axis. So I've computed optical flow, dense optical flow with OpenCV using Fehrenbach's method, and I've taken the logarithm of a normalized optical flow and applied a color map to visualize it. And it turns out we could actually get a pretty decent estimation for motion. And in this case, we're going to assume the stationary camera just like we did in part 1, but this is actually a stepping stone into more advanced methods where the camera is moving and is more complicated. So we'll cover those in a later tutorial, but for now we're just going to focus on the same case of a stationary camera. So before we get started, let's just show what the outcome is going to be. So here's the final motion detector. And you can see it's pretty noisy. We still detect clusters of objects. It's very hard to break these out. And we'll see why. We'll see some of the things that we could do to improve it. We're not going to work too hard for it because there's actually a better method than optical flow. This is just to be a stepping stone into more advanced methods. So let's get started. So we have our imports. I've already done these. I have JPEGs of traffic data. I've plotted these two images for us to work with. So the first function to go over is the flow function. So we're going to take in two image frames that are sequential, and we're going to convert them to grayscale. So they're BGR, and we want to get grayscale. The next thing we want to do is we want to blur them, and I find that it just makes the outcome of the optical flow just a little bit better, but that's optional. You can play around with it and see what kind of effects that makes. And this next one is where we actually calculate optical flow in OpenCV using Fehrenbach's method. That's not what I wanted. So OpenCV calc optical flow. It's always a good idea to view the OpenCV docs. So you can see what. Well, no, this is not what I wanted. So that took me to object tracking for some reason. So right here, this is the basic tutorial on how to do it. If you're interested in what these parameters are, I'm not going to go over them in detail, but you can change these to increase the speed, change the quality of the flow map. You can use less pyramid levels to increase the speed. You can resize this image to half size to increase the speed. It just depends on what you want. So I've played around with these and found that this combination gave me some pretty good results. So I'm going to keep these here. And this next one is a get flow viz. This basically helps us visualize the flow in a nice way. So this has come straight from the OpenCV docs. The only difference is I converted it to RGB as opposed to BGR since I'm going to display it with Matplotlib. So now we want to compute the flow. So in this cell right here, divide by 0. Okay, so sorry, did not have the images I thought. So in this cell right here, we actually do the first step right here. We compute the optical flow, and then we separate it into magnitude and angle. So the next step is going to involve obtaining a motion mask from the magnitude right here. So to do that, we simply threshold it with a value, and we'll go over this in a little bit, and we get a mask of 0s and 255. It's a NumPy UN8, and this allows us to do morphological operations to clean it up a little bit. So we're going to do an erode right here. So we're going to trim everything down, and then we're going to do an open. So what an open does this. It gets rid of all this speckle noise and maintains the size of the ones that don't get eliminated. And the reason for that we do the erode and not just two opens, is because we want to reduce the blob size So we have these blobs right here. The first erode actually takes down the blob size of all of these, and if anything is stuck together, it can eliminate that. So we want to be careful of this. We don't want to erode things too much. And right here, this didn't quite do the trick with eliminating these two cars in a truck. They're going to be detected as a single cluster in this frame. So the next thing we want to do is we want to do a closing operation. So this is the closing operation. It just fills in the holes inside of the solid blobs. And we could see that right here. If we could do some more iterations, we would close these, but we're not going to overdo it for this one. So that's all for the mask. And now for the motion threshold. So instead of using a static threshold comparing every pixel in our magnitude right here to the same value, we want to use some prior information. So if you look at these pictures right here, frame 1 and frame 2, you can see that at the bottom where the cars are closer, they appear larger and they have large pixel displacements. You can clearly see from frame 1 to frame 2 that this car has clearly moved. But back here, these cars don't move a lot. And you can see that their flow values, the magnitude of their flow values is not as high, especially, way back here as opposed to the middle and up front. So the reason for that, we want a lower movement threshold back here on the top and a higher movement threshold at the bottom. So we're going to use a linearly changing threshold from top to bottom. So we're going to start at 0.3 and we're going to go all the way up to 1. So this is what this piece of code right here does. I make a column that goes from 0.3 to 1 linearly spaced through 1080 points, and then I repeat it for as many columns as the image frame, and I get this motion threshold right here. So that's the motion threshold I pass to the motion mask, and I use a kernel of 1s. I just use the default kernel 7x7 for the morphological operations, and this is what we get right here. And here is the scaled output of the visualizer. The reason I scaled it by 50 is because you can't see anything if you don't. So if I don't scale it by anything, you don't really see a lot. So that's why I did that. And even though it saturates some of the stuff, it still helps us see everything. And we can see that this estimate is still noisy. Now these noisy estimates, they come from, possibly camera vibrations or even just imperfections in the optical flow algorithm, and also image noise that happens. So now moving on. So the next thing we want to do is we want to get the detections from this motion mask. So we want to send the information that we have detections into actual bounding boxes for further processing. So that further processing is outside the scope of this video, but it could be a tracking algorithm. It could be something like analyzing cells and biology. It could be customer analysis and marketing, or anything like that. So we want to draw contours around these right here. And once we get a contour, we can actually use OpenCV to draw a bounding box. So we could use OpenCV for both of those things. And we did this in part 1, but there's a little bit of a twist for this optical flow. We have other information that could actually improve the quality of our detections, and that is the angular flow. So we've only used the flow magnitude to get detections, but what if something is not a real target? What if it's not a real moving object? Well, a real moving object is going to tend to move in the same direction. So if we plot the angles right here, I don't know that we're going to see anything, but it's kind of hard to visualize the angles. You can't really, maybe if I saturate it, multiply it by 10. Yeah, it's really hard to see it, so maybe, well, let's try this right here. So angles less than MP pi divided by 4. So we can get something. We can see that we have some angles right there. We'll do pi divided by 2. I don't know. It's hard to see, but you can barely see that there's kinds of clusters right here with each of the cars, and they're different colors. So let's change the C map. Let's see if we could do, no, not at all. I have some color maps up here. Let's try Let's try, I'll just copy all these. Let's see if we can visualize this. So HSV is not good. We can try flag. That is not good. Alright, last try these two right here. Oop. These work for the magnitude, but not for the angle. Okay, well you can kind of see right here, this is very dark blue for the cars coming towards us and very light blue for the cars coming away from us, and we can't really tell there. So each of these objects is going to have a different angle, and we're going to want to use this information to determine whether a target is real or not. So what we could do is we could take each detected contour and see if the standard deviation of its angle of all the pixels that are contained in it is greater than the standard deviation of some threshold. So the threshold we're going to use is just going to be the standard deviation of all the angle pixels in this angle map right here. So, and we're going to multiply it by a factor. So STD gives us the standard deviation, and then we could scale it by, say, 3 or something, or maybe just 2. So if the standard deviation of our target right here is greater than that, that means we have a bunch of pixels going in all sorts of different directions, and it's probably not a real object. So that's the main approach for the function below. And it turns out for the stationary camera, this doesn't really matter that much. This really comes into play when you have a moving camera. This is going to be a big deal then, but for now, we're not going to see much improvement. So the code works like this. We use OpenCV to find the contours. Skipping ahead, we iterate through all the contours. We use the OpenCV bounding rect function to get the bounding box information and compute the area. And then now we want to get the second factor. So if our area is greater than a predefined threshold, we want to consider it as a detection. But the second thing we want to consider is the angle that we just talked about. So the way to do that is we draw the contours on a temporary mask that we made right here, and then we can calculate the flow angle by taking the numpy not 0 of the temporary mask and indexing that into the angle that we pass in to here, and I didn't pass it into here, so I'll use this one for a single function. So then we take the standard deviation of our flow angle and compare it to our angle threshold, which what we did was I took the standard deviation of the angle, multiplied it by a factor of 2, set that to our angle threshold, and if this is less than our angle threshold that we made right here, we're going to consider that as a detection. So let's go ahead and get our masks. This is the same result. We have our get contour detections. So this is our basic one that we used in the original video in part 1. Oh, wrong one. So we basically get the same thing. And in case you're curious, in the imports, I have this motion utils thing where I put all the previous functions we used in the frame differencing tutorial. I put them in a PI file so we could use them for future projects, and they're going to come in to great use when we start doing other stuff. So that's all that is. Same stuff we covered in the first video. They're just in this PI file, and I import them. And the first line like this. I just went ahead and dumped all the functions in here. So back to this. So now we're going to want to do non-maximal suppression. So a non-maximal suppression does is it moves bounding boxes with an IOU threshold. That is a bounding box overlap threshold greater than a specific threshold that we define. And we also added a twist on ours. We move bounding boxes that are completely contained within others. So if our non-max suppression is working correctly, we should be able to move this bounding box entirely. So let's go ahead and perform this. So we can see that we had 11, now we have 10. Let's see if it actually removed that box. And it did. So the reason why we do this is because we know that these things are going to be stuck together, and we generally want clusters of moving objects. In this case, we're not going to be able to count the detections with this method. This is only for just to get the experience that we could use this for future methods. So let's go ahead and put all this in a pipeline. So we're going to compute the optical flow. We're going to get the magnitude and angle. And I actually use an underscore here for the angle, so we don't have to worry about it because it turns out it doesn't do us that good. We're going to get our cleaned up motion mask, and then we're going to get our initial proposed detections without using the angular information. We're going to separate the detections into bounding boxes and scores, and remember that scores in this case are the same as our area. I recommend you go back to the first video and watch the part that covers non-maximal suppression and the motion mat and the detections for motion masks if you want to understand that a little more. Basically, a normal object detector always has a confidence score, especially if it's a deep learning based object detector. And it uses that confidence score. Is typically used for non-maximal suppression, but in this case, we want to use our areas for our confidence scores, or just our scores. And the bigger the area, the bigger the score, because we want to prioritize the larger boxes as opposed to detections that are more confident. So that's what we're using that for. And then we run our non-maximal suppression, and once again, it's almost the same as any other non-max suppression algorithm, except this non-max suppression algorithm removes bounding boxes that are contained entirely within larger bounding boxes. So that's it. Now we can run this on videos, so we can get the frame. So we set our motion threshold, define our kernel for the morphological operations, read 2 frames at a time. We get our detections using our detection pipeline. We could draw bounding boxes, and we can plot, save, and close. And with that, we could actually make a GIF, which I have right here. And remember, this create GIF from images, I've actually put that right here, so we could actually create a GIF with a single function. And here's the outcome. So, all right, that's all for this one. And the next one, we're going to use a better method that's going to be able to disambiguate all these cars right here, and even the smaller ones, to the extent that a neural network like YOLO probably won't be able to do as well. And that's called background subtraction. So we'll go over that next. I'll see you on that one.